Hidden within the gravitational tug-of-war between Earth and the Sun are 5 invisible spots where a spacecraft can simply sit still, perfectly balanced in space. Lagrange points are locations in space where the gravitational forces of two large bodies create a stable balance. They are named after Italian-French mathematician Joseph Louis Lagrange, who discovered them mathematically in 1772. There are 5 Lagrange points in any two-body system, labeled L1 through L5, each with unique properties. At a Lagrange point, a small object can maintain a stable position relative to the two larger bodies without using fuel. This makes Lagrange points extremely valuable locations for parking spacecraft and telescopes for extended periods. L1 sits directly between Earth and the Sun, allowing continuous observation of the Sun without any interruption. Solar observation spacecraft positioned at L1 can monitor solar activity around the clock, providing early warning of solar storms. NASA's SOHO spacecraft has operated at L1 since 1995, continuously studying the Sun's surface and atmosphere. L2 sits on the opposite side of Earth from the Sun, remaining permanently in Earth's shadow relative to solar radiation. This location provides an unobstructed view of deep space while remaining shielded from the Sun's intense light and heat. The James Webb Space Telescope operates at L2, approximately 1.5 million kilometers from Earth. This distance is roughly 4 times farther than the Moon, yet remains gravitationally connected to Earth's orbital position. Webb's massive sun shield, the size of a tennis court, blocks heat from the Sun, Earth, and Moon simultaneously. This shielding keeps Webb's instruments at extremely cold temperatures necessary for detecting faint infrared light from distant galaxies. L2 was specifically chosen because it allows Webb to maintain constant orientation away from the Sun without complex maneuvering. The Planck spacecraft and Gaia mission have also used L2 to study the cosmic microwave background and map stars precisely. L3 sits on the far side of the Sun, directly opposite Earth, permanently hidden from direct observation. This location is less useful practically since spacecraft there cannot communicate directly with Earth due to solar interference. L3 has appeared frequently in science fiction as a hidden location for a mysterious counter-Earth or secret base. In reality, no spacecraft currently occupies L3 due to its impractical position and lack of scientific advantage. L4 and L5 are unique among Lagrange points, forming stable triangular configurations with Earth and the Sun. These points sit 60 degrees ahead of and behind Earth in its orbital path around the Sun. Unlike L1, L2, and L3, points L4 and L5 are inherently stable, meaning objects there naturally stay in place. Small perturbations at L4 or L5 tend to correct themselves, unlike the other Lagrange points which require active correction. Jupiter's L4 and L5 points host thousands of asteroids called Trojan asteroids, trapped by the planet's gravity. These Trojan asteroids have remained stable in these positions for billions of years since the solar system's formation. NASA's Lucy mission is currently studying several of Jupiter's Trojan asteroids to understand early solar system history. Earth also has its own Trojan asteroids at L4 and L5, though far fewer than the thousands found at Jupiter. Scientists have proposed using Earth's L4 and L5 points as potential locations for future space stations or colonies. Science fiction author Gerard O'Neill famously proposed massive rotating space colonies located at these stable points. These theoretical colonies would use rotation to simulate gravity, housing potentially thousands of permanent residents. The L1 and L2 points require small amounts of fuel for occasional correction, since they represent unstable equilibrium positions. Spacecraft at these points orbit in what's called a halo orbit, tracing a loop around the Lagrange point rather than sitting exactly on it. This halo orbit design keeps spacecraft antennas pointed away from the Sun's interfering radio noise while facing Earth for communication. Lagrange points exist in every two-body gravitational system, including the Earth-Moon system, not just Earth and the Sun. Future lunar missions may use Earth-Moon Lagrange points as staging areas for spacecraft heading to and from the Moon's surface. NASA's planned Gateway space station will orbit near a Lagrange-related position in the Earth-Moon system. This strategic positioning allows Gateway to serve as a convenient waypoint for missions traveling to the lunar surface. Understanding Lagrange points required solving what mathematicians call the restricted three-body problem. This problem, involving the gravitational interaction of three objects, has no simple general solution in most cases. Lagrange's specific mathematical insight revealed these 5 special points as elegant, calculable exceptions to that complexity. Today, engineers rely on Lagrange's centuries-old mathematics to plan some of humanity's most sophisticated space missions. These invisible points in the emptiness of space have become essential real estate for humanity's greatest scientific instruments. Nearly 250 years after Lagrange first calculated these strange points on paper, humanity's most powerful telescope now sits balanced within one, quietly staring into the deepest reaches of the universe.